The last speaker for this session is Andrea Montanari, who's the Robert and Barbara Kleiss Professor in Departments of Electrical Engineering, Statistics, and Mathematics at Stanford University. And Andrea is going to tell us about minimum complexity interpolation in random features models.
Okay,
Andrea,
thanks a lot, Peter. And yeah, so let me start right away. Can you hear me?
Yes, we can.
Okay. So this is joint work with Michael Celentano, who was a student in my group and just graduated, and Fyodor Misyakiewicz. And so I'll talk about this paper that we wrote a few months ago, and we're still working. There will be an introduction, a definition of the problem, and a conclusion. Yeah, okay, so my motivation comes from trying to understand large two-layers neural networks. So this is neural networks with one hidden layer in which I have an input dimension D. So I have an input dimension D. I have a first layer weight Wi and the second layer weight AIs, right? And in between, I have a bunch of nonlinear activations, sigmas. And the number of neurons is capital N, and the capital N and D are the two parameters to remember. And of course, a natural way to write an infinite width limit, so capital N to infinity limit of this kind of network is to replace the sum by an integral. So I need an underlying measure. So I measure mu on RD, and then I have an integral over RD, and I replace the second layer coefficients by a function A of W. Okay, and actually for this talk, I will generalize slightly the setting. Oh, this got, I think I lost the connection. I'll generalize slightly the setting, and instead of activation functions that depends on a scalar product, I can deal with a slightly more general setting in which the weights belong to a general probability space on which I have my measure mu, and this activation function is replaced by a featurization map that goes from X, which is the input space, to times omega to R. So it doesn't need to depend only on the scalar product. So I don't know how to give a name for this. Say this is generalized two layers neural network or features model. Okay, so models of this type, of course, have been either implicitly or explicitly studied in the approximation theory literature. Here is just to I will not review this literature in any detail, but just to mention this connection. For instance, one way to do approximation theory is that you define a function space that is the space of these infinite width networks, where, for instance, you have a finite L2 norm on A, and then you define the space of finite, two layers network, and then, under a number of assumptions on the measure mu and the activation function, the featurization map phi, you obtain a result of this type that, this space of infinite network is dense in L2. Here I have an underlying measure P. This is my measure on the data. And then, if you give me any function in this space F2, then I can approximate it arbitrarily well with the finite width network. Namely, for instance, this is the bound, the L2 distance between the two goes down like 1 over the number of neurons times the L2 norm of A. This is very easy bound. This is what's called the Murray argument. Okay, so so here I want to ask the following questions. I mean, once you write this kind of infinite models, there are two natural questions. How can you learn this infinitely wide neural network for data, and what are its generalization properties? And the point that I want to emphasize is that answers to both of these questions depend on how you define the complexity of A, right? How do you regularize for A? And there is one example that is very well understood, is the example in which I regularize for A, or I measure its complexity by its L2 norm. This is the one that somehow implicitly I mentioned this. So the L2 norm of A is, of course, the integral of A squared over mu. And this induces a norm over the space of functions. The norm of the function f will be the infimum of all the L2 norm of A, such that f can be represented as a combination of the feature map times A. Now, this norm over the space of function is completely equivalent to a reproducing kernel Hilbert space norm. So, in fact, this is the RKHS norm for this kernel, the kernel that is the expectation of phi with respect to the measure mu. Okay, so if I take this model and I decide that the right measure of complexity is the L2 norm of A, then I get kernel methods or RKHS methods in general. And of course, this is a very rich type of model and a very interesting type of models, and includes things that have been very interesting and very much studied over the last few years because of connections with very large 2 layers or multi-layers neural network in the so-called neural tangent or a lazy regime. Namely, for instance, if you take a 2-layer neural network and you linearize around the initialization, and then you take the infinite width limit, you obtain that the model is well approximated by this kind of linear model, where now this is very similar. So this should be sigma prime. This is very similar to what I was writing before, except that the function A of W is being replaced by this. But as long as, again, complexity is measured by the L2 norm of B, then this is still a kernel method, and then it is equivalently represented for another function sigma tilde in the way I described before. And multi-layer fully connected neural network in the neural tangent regime fit the same framework. Okay, so what are the pros and cons of sticking to this measure of complexity? The pro is that for free that this is always solvable in polynomial time because of the representer theorem. So despite being, optimizing over A is an infinite dimensional problem, you know that it can be solved in time polynomial in the number of data points. The con is, of course, that it suffers the curse of dimensionality. Okay, I want to take a pause to discuss briefly the curse of dimensionality in this context. And okay, I'll do it stating a result from our work, but there are many equivalent ways of looking at this. And okay, the result is for data uniform on the sphere, responses are some function of the input data, and there is some technical assumption on sigma. So this is a result of a couple of years ago, says that if you do kernel ridge regression okay, the important thing here that I didn't write is that here I'm taking a kernel that is an inner product kernel. And in this setting, if you take the W that are uniform on the sphere or rotationally invariant, then the induced kernel is an inner product kernel. And the result says the same if you take an inner product kernel and you try to fit a function f star using a kernel ridge regression for any lambda in a certain interval that includes 0, then if the number of data points scales polynomial in the dimension, the risk of kernel ridge regression is the projection of the target function onto polynomial of degrees bigger than L. And if you're worried about this choice of the regularizer, no inner product kernel method can do better. Okay, so this result means that if you look at the risk as a function of the number of data points versus number of dimension, you get this kind of staircase picture in which every time this number passes an integer for very large n and very large d, you learn one degree polynomial of 1 degree higher. Okay, so what I want to emphasize here is an easy corollary of this is the following. If my target function is a function of a one-dimensional projection of the data, and if this G star, so G star is a function real to real, if G star is not a polynomial, then as long as the number of data points is polynomial in the data, the error is bounded, of kernel ridge regression is bounded away from 0. And the error of any kernel method is bounded away from 0. And this is a curse because, on the other hand, functions of this type are very low complexity. They can be learned from all D-log D samples. Okay, a different point of view on the same example is the following. If I have this kind of activation function, again, the classical inner product activation function, and my target is, here I should have written, okay, this is the same target. Target is sigma U0 x, or W0x, I should write, for some W0. Then, of course, my target function can be written as an integral, but my target measure mu star is a Dirac delta. And of course, this is singular. I mean, this doesn't belong to this space where I'm constraining the L to no. Okay, so this example and this way of looking at an example suggests a natural modification of our scheme. That is, okay, what I'll do is that I measure complexity instead than by the L2 norm by putting here a general convex function. Okay, and so I'll try to minimize this objective. This is a loss function. Sorry, there shouldn't be a square here. And this is a loss function that depends on the data and my model, my prediction, and this is a complexity measure that I used for generalizing. And of course, the question are, what are these generalization problems? And the question that I want to focus here is a different one, is how do I optimize this efficiently?
And Andrea, your slides seem to have stuck.
Okay, this happens, I'm afraid, when.
There we go.
Thank you, Peter. And I must say here, somehow my slides dropped some citations here because this idea of putting another regularization is not new. In particular, okay, what we would hope to do is putting rho to be the absolute value so that we get the one norm of A. And again, this idea is not new, is in, is sometimes referred as convex neural networks, and this was a paper by Benji et al. Is present in work by Peter of the 90s and was studied by Francis Bach and others more recently. So here, what I want to focus on is this second question, not the generalization probability, but the optimization question is, can we optimize this efficiently? And the hope comes from the fact that this objective is convex in A. But the point is that it's an infinite dimensional problem, and if I could solve infinite dimensional convex problem, I would solve P equal empty. Okay, so we can always reduce this optimization question to an interpolation question by the usual trick. We can first minimize over the value of the function at the data points and then optimize over those values, right? So the optimization problem given the value of the function at the data points is this one. So our optimization question reduced to the following problem. Can I do the following? Can I do minimum complexity interpolation? So I want to minimize this objective subject to I achieve certain value of my function on the data points. So if all of my motivation, so far was basically motivation, if that was boring, now you have a nice mathematical problem that is, can I solve this problem? this optimization problem. Okay, and okay, so what we do in this paper is, the one of the few obvious things that you might try to do is discretize, right? Okay, so how do I discretize now? The deal here is that I want to do in a way that is dimension independent, and for this is very convenient the fact that I have a reference measure mu. So the way to discretize naturally is that I go back to random features. So I sample Wj with measure mu IID, and then basically I replace mu by the empirical measure. So all the averages with respect to mu are replaced by empirical averages, and I solve this problem. Okay, now I stated the problem, I stated the method. Now this I can solve in time polynomial in capital N. Okay. So what I'm hoping now is that I'm able to get a good approximation is of the original problem by taking n that is polynomial in small n than in the sample size. If I've done that, then I have a polynomial time algorithm. Okay, so now for doing this, we need a bunch of assumptions, and let me go over the assumptions because, of course, as always, they are the crux of the matter. So I have I evaluate the features at my n data points. I call this the feature vector phi. This is a random vector because W is random, and psi is just the whitened version of the same object. A crucial role is played by this matrix K that is just the empirical kernel matrix, the kernel matrix on the data points. So this is an n by n matrix. Okay, so the assumptions are the following. Okay, the data points are in a certain ball. This is the right scale. This feature vector whitened are sub-Gaussian when you draw W with its right measure. This featurization map is Lipschitz in X, where the Lipschitz constant is itself can be a random variable, doesn't need to be uniformly bounded, but it needs to be sub-Gaussian for our Prof to go through. I think there is no further here. And okay, 4 is the really tricky condition, is a small ball condition that says the following, that if you take any two vector, V1, V2, so any two-dimensional projection of my data, of my psi, of my white and feature vectors, this is outside a small square of size eta with probability at least delta. So eta and delta can be any arbitrarily small constant. In fact, I think eta can, some of them, one of them can even be inverse polynomial. This is implied by it's weaker than the more standard small ball condition that will be, so this is implied by this 1/2 1 plus delta prime for some positive eta and delta prime. Okay. Okay. So if you give me all of these assumptions, then what we prove is the following. Take for simplicity this complexity to be x to the p, and p between 1 and 2. Let q be the dual of p. And then what I look at the L2 error of the model that I obtain. So what is the rationale for looking at this metric? Okay, what I'm interested really is f of x. If the model that I'm interested in using this method to learn, to do machine learning. So to learn a function f from data, right? So I have in mind that I have an ideal method that computes this, and then I compare it with the discretized method with a random feature approach that instead computes this function, and I compute this difference in L2. So this is L2 of the data. So this distance is this distance, okay? And what you obtain is that this is upper bounded by, okay, this constant depends on all the constants in the assumptions, basically. And then this goes to 0 with n, with the capital N, and increases with the number of data points. So we obtain that if capital N is basically bigger than n square, so what you need is n square n to the q over 2 plus 1. So it's q plus 1 over 2. If n is much bigger than this, then we are in good shape. We get a good approximation. Okay, so we obtained what we wanted. The number of random features that we need to get is polynomial in the sample size for any norm p. Now, two weak points of this result that some of you will have noticed. First weak point, this doesn't include p equal 1. That is what I started with, was probably the most important corner case, right? And well, I think there is a fundamental reason for that. I think that for dealing with p equal 1, you need really to make other assumptions. Otherwise, you would solve some computational lower bounds. Okay, so without any assumption on the data distribution, I don't think it's possible to do p equal 1 in polynomial time. And the second thing that people might have noticed is that, okay, this is in particular requires the number of features to be bigger than the number of data points square, even for p equal 2. While for p equal 2, we know, in fact, that n bigger than n or much bigger than n is, so number of features much bigger of data points, a liter over parameterization is sufficient. This is, for instance, enjoying to work with Theodore and the Song May. So these exponents that we get here are not optimal. And in particular, they are not optimal for p equal 2. In the case p equal 2, the proof can be fixed, but in the general case, we don't have the optimal exponents. Okay, so this is one figure, only figure of this talk, unfortunately, but I think it's a nice figure in which what we plot is, okay, so the first two lines are for p equal 2. So p equal 2 means, again, kernel methods. So in this case, we have a well-defined capital N equal infinity limit that we can compute using the standard kernel trick. And this is the dashed line. Okay, so this is the infinite width kernel. And the random feature approximation is the red curve that approaches it. Okay, so I should say what I'm plotting here. Here I'm plotting test error for a problem in 30 dimensions and 150 data points. And the function that I'm trying to fit is the kind of curse of dimensionality example. Okay, so I'm taking the function that is difficult for kernel method and try to fit there. And I see that kernel method, when you increase number of features, that the random feature converges to a limit, and this limit is well described by the infinite width kernel. And now we reduce p, and we observe that we can quite easily beat this limit by a non-negligible and not entirely negligible amount. So this is for 1.5, and this is for 1.2. And okay, we even try to solve p equal 1, even if we don't know what the limit of that will be. But so what you observe at 1.5, 1.2 is that we beat the kernel limit, and this seemed to saturate at some level. Okay, whatever this this simulation say, but we seem to be reaching the asymptote. For the p equal 1, interestingly, we don't see them saturating, but interestingly, you can beat the 1.5 and the 1.2. Okay, perhaps 5 minutes I have, so let me say one word about the proof idea, because I think it's an interesting kind of problem. So again, the infinite n equal, the original interpolation problem is this one. We want to minimize this objective given that you interpolate data points, and then we want to approximate it by this one. Now, the natural reflex that anybody would have is, okay, we have here a problem over the W over, and then we replace W over, with the measure mu, we replace it by the empirical measure. So here what we are doing is replacing this by the empirical measure. So we might as well use some uniform law of large numbers kind of technique. Now there is a problem here is that, okay, this is not both, but the original, the problem is this problem live in different spaces, okay? This problem lives in an infinite dimensional space A, and this is in a finite dimensional space, and the infinite dimensional is infinite dimensional, so it's a bit difficult to do uniform convergence in that space. Okay, so what we resort to is looking to the dual, which is a natural idea. So it's a problem in which I fix the sample size, and instead I let the width of my design matrix basically or the dimension of my feature go to infinity. So I think of the sample size as fixed, and we are letting the number of features go to infinity. So what is the dual? The dual looks like this in infinite dimension, and the optimization parameter is lambda, that is Rn. So it's sample size, and rho star is just the Fenchel dual of rho, and the finite dimensional approximation is this one. Okay, now we want to approximate this by this. Okay, once you get to solve the dual, then you can compute the predictor in this way. So the predictor is the map, and then you have a certain nonlinearity applied to lambda times to phi. In the case of kernel method, this S is the identity, and then you get the usual representer theorem. Okay, so this is very nice if you studied kernel method, because it's a minimal modification to kernels that makes them very difficult to work with. Okay, and so how that was our proof go? We have these two problems. Now these are problems in some fixed dimension, large fixed dimension, and then we want to prove that the optimizer are very close to each other, and then deduce from that that there shouldn't be this, that the two functions are very close to each other. Okay, and we do this by basically proving two properties. So now this is our objective function in finite n. We want to show that the optimizer concentrates to the optimizer of the expectation. This is a concave problem. There is, an infinite limit. So this is f. Perhaps this is fn, and the optimizer of f is somewhere here, and the optimizer of fn is here. And we want to show that the two are close to each other. So what we prove is two things: that the gradient of the green function of fn is close to 0 at the optimizer at the infinite width problem. And then we prove that the Hessian is uniformly upper bounded in this case, because we are looking at a maximization problem in a certain region that includes our optimum. Okay, so we use kind of strong convexity in a certain restricted region. Okay, so all the work is basically in trying to prove these two properties. Okay, quick conclusion. So the motivation, my motivation for this, or the way I got this, is that this equivalence between neural network in the linear regime and kernel methods, and this can be kernel methods. These are features model with quadratic penalty, and so it's natural to introduce another inductive bias that is not the ridge bias, and we prove that this can be computed efficiently for a certain class of penalties. And I should have mentioned that in the theorem, in my statement, I took rho equal x to the p, but okay, we have a somewhat more general result in the paper. I guess that's all.
Great, thanks very much. I'm curious about the computationally difficult limit. As p goes to 1. You mentioned that the dependence between the capital N and N there was evidence when P is 2 that this is loose. What do you know about the other limit? You know, as P goes to infinity, is the dependence on Q? You know, do you know anything about the
yeah? So this is going. So Q is going like saying n to the 1 over P minus 1, or something like that for,
right? Yeah,
I mean, up to a factor, perhaps is 2 over P minus 1 or something like that for P going to 1. So I would think I mean, I don't know. I mean, the right answer is that I don't know really. I mean, my pessimistic side tends to think that this is the more or less the tight thing with P. But simply because typically when you have curse of dimensionality, you get this kind of 1 over P minus 1 kind of behavior. So that then you are forced to take P to be 1 plus 1 over D, and then you are in bad shape. But okay, I think that, yeah. So my guess is that if you take P to be 1 plus something, then you still get, and you try to learn arbitrary function, you get in terms of sample size, now generalization error. Now, by using this model, you might get a smaller exponent in the exponential complexity of learning. Sample complexity.
Right. Yeah, go ahead, Jens.
I have a question, and maybe it's a little bit off, but I was very interested when I read and heard about Rotskopf and van den Einden looking at the training of the infinite one-dimensional layers, where one could kind of get a partial differential equation for the measure of the evolving weights. And I was wondering, for the 2 layers that you have been playing with, if there is something analogous, if the training of these things could look like a 2-variable PDE. But I'm not so sure about the question.
Yeah, so I have several answers to this question. First answer is that, yeah, so this is what I call 2 layers, is perhaps what you're referring to 1 layer. So it's 1 hidden layer. There is this.
1 hidden layer. Okay, sorry.
Yeah. And the other thing is that, okay, so, but I have another answer. Okay, we actually wrote a paper at the same time as Eric and Rotskopf on the same thing. Third question is, there are generalizations for multi-layer of this formalism. There is I think one good paper is a paper by Huy Thuy Phan and Phan Minh Nguyen, who are Phan Minh was a Stanford student, Huy Thuy is still a Stanford student in mathematics. They have a generalization for multi-layer, but it's not a PDE. It doesn't use a partial differential equation. Probably there is no way to write a partial differential equation. It uses a more abstract kind of thing, but it computes the limit of infinite width for multi-layer fully connected.
So can I ask again? I mean, I should of course read and will, but so you think it is not it would be very tempting to think of it as a 2-variable PDE for 2 layers, 3-variable for 3 layers. Is that wrong? So do they have something?
That's wrong.
It's wrong. Okay, thanks. Yeah, good. Thanks.
All right. Any other questions? Sarah, did you have a question?
Yeah. So you look at the computational problem. Thank you for the nice talk. Wonderful.
Thank you.
You look at the computational problem, right?
Right.
So, but if you look just at the discretized version and then look at the approximation error, do you get different conclusions? Right? If you're just interested in generalization error,
right?
Then the discretized version has an approximation error, which you don't know, of course, but
yeah. So this is what I think. I mean, okay. So the question is, if I take, in large dimension, can I approximate better functions using this these LP norms, right? I mean, if I take whatever, I'm trying to interpret your question. So your question is, okay, if I take this P norm of, okay, this P norm less than R, let's say, can I approximate, and now I take F star to be a kind of ridge function, for instance, you know, g of W0 times x, can approximate better f star within, so what is inf over f star minus f of ba dot a over a2 over a p less than r. Okay, so your question, I think, is
Yes.
something like this. I mean,
Yes.
that is what you need for doing the generalization error.
Yes.
And this is, I think, what I was mentioning quickly. I think that you still have the curse of dimensionality for every p bigger than 1, for any fixed p bigger than 1. But I think that, yeah, so, but I think
so for
that
p equals 1, it would be nice, right?
Yeah, for p equal 1 would be nice, but for any p bigger than 1, you're in trouble, right? So,
Yeah.
but I think that, okay, I didn't think very much about this, but I think that if you ask for me for the sample size to achieve a certain generalization error, so for all of these methods, we go exponentially in the dimension. But I think what you might get is that the coefficient in the exponent might improve with p. Yeah. So you still have curse of dimensionality, but you have a better. Oh, why? I noticed that I'm writing, but you're not seeing what.
So I don't think with p equals 1, you don't have, well, this little curse of dimensionality, but not so bad. If you assume this
I see.
L1 norm to be 1, you have this convex hull type of arguments.
Right.
So that the complexity is small.
Mm-hmm.
Yeah. Okay, thank you.
So, but yeah, it's a good question. I mean, to me, it seems that, okay, that what simulations show is that this doesn't have a negligible effect, doesn't have a completely, I mean, it's not a bad idea to try to minimize p equal 1.5, but yeah, I don't have a theory of that.
Okay, thanks.
All right. Jason asked one more question in the chat that seems very closely related. So perhaps we should stop the discussion there. Thanks again, Andrea, and thanks. Big thank you to all of the speakers today. Thanks all.